Welcome to lesson 4 of topology. In this lesson, we're going to talk about orientable surfaces, which is a topological invariant. Recall from the previous lessons, we talked about different objects that had the same Euler characteristic. For example, the cylinder, the torus, the Klein bottle, and the Mobius strip all had an Euler characteristic of value 0, but they were different topological objects. So we need another or other invariants in order to distinguish and classify the different topological objects. And one such invariant is called orientability, which we'll talk about here in this short lesson. Here's a quote from Wikipedia, which I'll read quickly off. A surface S in Euclidean 3 space is orientable if a chiral two-dimensional figure, and this term chiral is not common, but it's a figure not identical to its mirror image. So you could take something like a clock, cannot be moved around the surface and back to where it started so that it looks like its own mirror image. Otherwise, the surface is non-orientable. So an abstract surface, a two-dimensional manifold, is orientable if a consistent concept of clock rotation can be defined on the surface in a continuous manner. That is to say that a loop going around one way on the surface can never be continuously deformed without overlapping itself to a loop going around the opposite way. This turns out to be equivalent to the question of whether the surface contains no subset that is homeomorphic to the Mobius strip. Thus, for surfaces, the Mobius strip may be considered the source of all non-orientability. So, a whole lot there in this paragraph. I'll just leave it there for a minute for you to take it in. But I'll give some examples and then a theorem related to this last couple of sentences here concerning the Mobius strip, and then we'll proceed to some other invariants in additional lessons. On the right, we have an example of a non-orientable surface. It's a Mobius strip, and we have an example of a chiral image. This is probably the simplest you can have, where you have a circle and it's just got an arrow going one way. And we start moving that around, keeping in mind that the Mobius strip and all surfaces are two-dimensional. They have no thickness, so what you see in the front you can also see from the back. And you notice as you hit the twist here, it's turning about, and then by the time you get back here, the little figure is going in the opposite direction. So that violates what you need to have happen for orientability. If you can go around a loop and come back to a starting point within a figure and the orientation of your chiral character changes, then it's non-orientable. So Mobius strip is the simplest example of a non-orientable surface, and in fact we have a theorem here: a surface is non-orientable if and only if it contains a Mobius strip. So we can actually use the Mobius strip to define orientability or non-orientability, and I took an example of how some writers do that. This is from the book Introduction to Topology, Pure and Applied, and they define a surface that contains an embedded Mobius band, you can use the word strip or band here, is called non-orientable. A surface that does not contain an embedded Mobius band is called orientable. So, as I say, the containing a Mobius strip or band is a way of defining orientability. On this slide, we have a strip similar to a Mobius strip, except it has two half twists. And the question is whether or not this is orientable or not. And there's two ways of looking at it. We can put our little chiral character in here. I didn't actually show, but you recall that from the last slide, we had a circle with an arrow going in one direction. And what happens is if you start here, it's going to flip once. You keep going around and it's going to flip again, but that'll bring it back to its original orientation. If you started here, it would flip once and then flip again. So no matter where you start and come back, the chiral character is going to be in the same orientation. So if you have two half twists, the figure is in fact orientable. And there's a second way of showing that. We can make a cut, then untwist the strip, and then rejoin exactly along the point, rejoin the points exactly as they were, and then reattach, and we get a cylinder, which, as we mentioned before, is orientable. So you may remember from an earlier lecture I talked about cuts not being allowed if you're looking for showing that two figures are topologically equivalent. But this is the exception I alluded to several lectures back then. You can cut and reassemble as long as you rejoin where the points are meeting exactly as they were before the cut. And that's what we did in this process here. So you may be thinking, well, what about 3 half twists or 4 half twists and so on? And we're going to talk about that in the next slide, but you may want to try to figure it out on your own before I actually give you the answer. In general, an even number of half twists in series, so one after another, will cancel each other out, and an odd number of half twists in series will reduce to a single half twist. So if you have an even number of half twists that's in a strip, you're going to have, or it'll be orientable, and if you have an odd number, it will be non-orientable. So that's when you have the twist in series, but you could have them in parallel like we have here, and then the question is whether or not these figures here are orientable or not. So let's look at the one on the left first. It has several half twists. If we go about the path here shown with the dashed line, we start with it going clockwise, still going clockwise, of course, here. And then as we're getting back to where we started, we're going to get that one twist, and it's going to make it counterclockwise. And so this is not orientable. We're able to find the path where when you follow that path, the orientation changes. So basically there's an embedded Mobius strip. This path here is an embedded, or highlights, I should say, an embedded Mobius strip. On the other hand, the figure on the right, no matter where you start, if you go around and come back, you're going to flip your chiral character twice and come back to the original orientation. So this is an orientable surface. What about the Klein bottle and the projective plane? Are they orientable? We can use the fundamental polygons to show that they are not. Let's take the Klein bottle first. We have this gray strip, and we'll do a half twist and then join the two B edges together. And I've drawn this so that the points along here exactly meet the points along here when you do the half twist. So basically you're introducing a Mobius strip into the Klein bottle as you construct it, and that means that from our earlier theorem 57 that it's non-orientable. And you have the same issue with the projective plane. When you do the half twist and join the two A edges together, again these points lining up exactly with those, then you're introducing a Mobius strip. So the projective plane is also non-orientable. Okay, so that's it for this short lecture. There's a few more related to surfaces, and please stay tuned and let me know if you have any comments.